Welcome back. So this is now our fourth lesson and we're moving on to the specification 4.3.2.1 and we're going to start thinking about moles. Okay, so I know you did a lot of this at Key Stage 3, so your understanding is actually really good, but just some key points to keep under your hat. Avogadro's number or Avogadro's constant, 3.01 times 10 to the power of 24. That's the number of particles of any element or compound or molecule in a mole of that substance, okay? The number of particles, it's always the same, which is why it's Avogadro's constant, okay? The coefficient refers to the big number. And remember, we used big numbers for balancing. If we go way back when we first started balancing equations, we're only allowed to change the big numbers, aren't we? And that's the coefficient. And that coefficient refers to the molecules, doesn't it? If you like, theoretically. But if we enlarge that up, it also refers to the number of moles, because the number of moles is, let's say, is the number of particles, and it's the same for every substance. And we relate it all to carbon 12, if you remember. Carbon 12 has got 12 in its nucleus. It's got 12 neutrons and protons. It's a ratio. So we're just looking at a ratio. So we could be talking about molecules, we could be talking about moles, we could be talking about grams. It is a ratio, okay? And if you can also remember, the mass of 1 mole is equivalent, there's another little mathematical sign there, equivalent to the relative formulaic mass or molecular mass, or the relative atomic mass, depending if we're talking about atoms or molecules, okay? So what does this actually mean? Do you like my mole? Okay, it's a bit simple, isn't it? But if we have got a mole of glucose and we put it on a balance, C6H12O6, let me just write in the missing 6, C6H12O6, it's going to be a big amount, all right? It's got that number of molecules in it, and each molecule has got 6 carbons, 12 hydrogens and 6 oxygens, okay? So we could weigh it on a balance. It's going to take up a fairly large volume, all right? And we could work out how much it's going to weigh, couldn't we, by adding up all the relative atomic masses. Now, within that molecule, there's water. So 1 mole of water is going to have exactly the same number of particles, but it's going to take up less volume, and it's going to weigh an awful lot less, isn't it? You're just going to add up the relative atomic masses of the elements there. And then hydrogen is within the water. Well, that's going to be much, much smaller again, all right? So just remember that. The mole, what's the constant about the mole? It's the number of particles. It's just the number of particles, okay? And then we've got our lovely magic equation that we use all the time. Mass equals Mr. Mole. Remember it. Mass equals Mr. Mole. Write it down when you get into the exam. Write it at the top of the page. And we'll put it into our equation triangle. The mass in grams equals MR, Mr., which is the relative molecular or formulaic mass, times the moles. And we can use N to mean the number of moles. We'll need to use that later when we look at concentration. But mass equals Mr. Mole. And then we can rearrange that, can't we? And you don't need me to do this, but I will anyway. If we want the subject as the relative molecular mass, we put our hand over the thing we want as the subject, and the triangle tells us what to do. So the relative molecular mass equals the mass divided by the number of moles. The number of moles is the mass divided by the relative molecular mass. Okay, so that's the basics on moles. Practice is on page 17 to 19, and that's it for lesson 3. I'll see you later for how we can use that to actually work out masses.